All right, so today we're going to do another statics example. So what we have here is another triangle. In this case, it's 5 meters tall and 3 meters wide. And we have 200 newtons of force hanging from point C here. Now notice the supports, the reaction forces at A and B are on a vertical wall. So my first step here, I'm going to get rid of the supports, and I'm going to replace them with reaction forces. So that was a pin. So I'll replace it with both an X and Y reaction force. So I have the reaction force at B in the X direction, and I'll have the reaction force at B in the Y direction. Now my roller is at point A, and notice the roller is on a vertical surface. So when I replace that, I'm going to replace it with a force that's perpendicular to that. So perpendicular to vertical is horizontal, and this is going to be my reaction force at A in the X direction. So I've replaced my my supports, my pin and my roller there, with the associated reaction forces. Now, my first step is I'm going to find the reaction forces. And to do this, I'm going to use the sum of forces in the X direction equals 0, sum of forces in the Y direction equals 0, and my sum of moments equaling 0. All right? So I'm going to start with each of those equations. I'll say my sum of forces in the X direction equals 0. Now, what are my forces in the X direction? Well, I see RAX, and it's going to the right, so we'll keep it positive. So RAX, and I have RBX, and it's also going to the right, so we'll keep it positive, plus RBX. Now I have two unknowns. I have both RAX and RBX, so I can't do anything with this one yet. So let's move on to the next one. I'll leave myself a little bit of room there so I can come back to it. Sum of forces in the Y direction equals 0. Now in the Y direction, I have a couple of forces. I have this one right here. This is RBY, and it's pointing up, so we'll make it positive. So RBY. And I have the 200 newtons going down, so we will make that negative, so minus 200 newtons. Those are our only forces in the Y direction, and if you look at the equation here, 0 equals RBY minus 200 newtons, you see we only have one unknown, and if we solve this, we'll find that RBY is 200 newtons. So I'll go ahead and write that on here. All right. Next, I'm going to take my sum of the moments around a point. Now, I like to take them around the point where the pin was, and that was B. So I'm going to take the sum moments around point B. So around that point. And notice RBX and RBY go through that point. So that means they don't create a moment, because a moment is a force times a distance. Both of those forces go right through point B, so their distance is 0, so their moment would be 0, so I don't have to worry about them. So the only things left that can create a moment, I want to check all my forces, and the only two left are RAX and the 200 newtons. So my sum of moments around B is equal to 0, and that equals what? So moments, a force times the distance. Let's do RAX. That's the force. And what's its distance from B? Well, if I come up here, that is 5 meters. So times 5 meters. Force, RAX, times distance, 5 meters. And this is going to cause the thing to rotate clockwise, so I'm going to make that negative. Next, I'm going to look at my 200 newtons. So plus 200 newtons times its distance from point B is 3 meters times 3 meters. And it also is going to cause things to rotate clockwise. So it also is going to be negative. All right. So I say that 0 equals negative RAX times 5 minus 600. All right. I'll move my RAX times 5 to the other side. So 5 RAX equals negative 600. And we find that RAX then must equal 120, which is just 600 divided by 5. Oh, negative 120. We don't want to forget that. Now, what does that negative sign tell us? It tells us that RAX is drawn in the wrong direction. So instead of going to the right, it should be going left. And it's 120. Okay? Now, since I have RAX, I can come back up here. Now, I do have to make a little modification to this equation. We originally had RAX going to the right. Now it's going to the left. We'll say it's negative again. So 0 equals negative 120 plus RBX. So RBX has to equal 120. And when I get all done, I want to double check. So I have 120 to the left, I have 120 to the right. That it cancels out. I have 200 down, I have 200 up. That cancels out. So everything so far looks okay. My next step, step 2. We'll do this each step in different color here. Step 2. Draw a free body diagram of each joint. So I have 3 of them. I have A, B, and C. So I want to come up, I look at point A right here, and I see that I have an external force, the 120 going to the left, and then I have 2 internal forces from the members it's connected to. So it connects to B and it connects to C. So I'll have force AB and force AC. Next, I'm going to look at point B. Point B has 2 external forces, 120 to the right and 200 up. All right. It also has the connection AB up and BC to the right. So force AB up, force BC to the right. Now, if you think this is a little bit crowded, that's fine. You can move the 120 to the left or the 200 down. You still want to keep them pointing the same way. I'll just show you how to do it here on the 200. So I can put it like this. If you feel better with it that way, that's okay. It doesn't really change anything. All right, now we're going to look at point C. Point C is connected to A and B, and it has 200 down. So point C has 200 down. It connects to B, so we have force BC, and we have force AC. Notice I still keep it AC, not CA. I don't want to switch it. I want to always keep these 2 letters in alphabetical order. That way I don't get things mixed up, and I don't fail to realize that AC and CA are the same thing. Okay? So step 2 is to draw a free body diagram of each joint. And we did that based off of our drawing. And we've made our joints. Next, step 3. Make the free body diagrams in X and Y only. All right. So the way we're going to do this, we're going to base this right off the 3-body diagrams we just drew. So I'll come here. The 120 is already entirely horizontal, so I'll leave it. Force AB is entirely vertical, so I'll leave it. And force AC goes down and to the right. So I'm going to make an arrow that goes down and an arrow that goes to the right. The down one is force AC's Y component, and the right one is force AC's X component. For B, we're going to do the same thing. Force AB goes up. The 120 goes to the right. Force BC goes to the right. 200 goes up. There were no diagonals on this one, so we didn't have to break down any forces. So it's actually the same as the last one, as up here. All right, C. 200 goes down. Force BC goes to the left. We don't have to break it down because it's entirely horizontal. And AC goes up and to the left. So we'll do force ACY and force ACX as our two forces. So a force that went up and to the left got broken down into a force that went up and a force that went left. So now we have, excuse me. So now we have our 3-body diagrams. Step 4. We are going to look for one unknown in each direction at each joint and solve it. All right. So, for example, on A, if I look in the Y direction, I have force AB and force ACY. That means there's two unknowns. I can't solve it. But in the X direction, I have 120 that I know goes left, which means force ACX has to be 120 to the right. And since it's pulling on point A to the right, that means it's in tension. So force ACX is 120 in tension. And remember, everything is on there twice. So over here's force ACX, it's 120, and it's in tension, so we know it's pulling away from that joint. All right? When you find your forces like this, they're actually going to kind of be pairs. You'll have one that goes to the right, one that goes to the left, that sort of thing. All right, but the big thing you want to remember, and the way you want to actually think about it, is it's in tension, so it's pulling away from the joint. So if it's in tension on point A, it's in tension on point C. Because if we look at the diagram up here, here's AC. If this was in tension, if it was a rubber band stretched between point A and point C, it would pull point C this way, and it would pull point A that way. So it pulls away from both of them. So that's what we see down here. It pulls away, and it pulls away. Now this is force ACX is in tension. Since ACX is just part of force AC, we know that all of AC has to be in tension. So that also means that ACY is in tension. I like to darken in the arrowheads just to confirm that to myself. So ACY is in tension. All right? So once we finish this for one, we want to keep repeating. So now in the Y direction, I still have two unknowns on A, and in the X, I have 0 unknowns. So I'll move to the next one. So on B, force AB, I have the one unknown in the Y direction, force AB, and 200. So if 200 goes up, force AB must go down. All right, so force AB goes down, 200. So there's force AB. I switched the arrowhead here. That means I'm going to switch the arrowhead here. So I've found one unknown and I solved it. And remember, you always use it twice. Now I start over, I repeat. So on A again, in the X direction, I have 0 unknowns. Both of those are known. In the Y direction, oh, now this changes things. I found force AB is 200. So it's 200 up because it's in compression. So force AC must be 200 down. So remember, I always write it twice. So force AC is pulling down away from the joint, so it's in tension. So over here where the other force AC is, it also must be pulling away from the joint with 200. And you'll see that when we did that, it actually canceled out the force that was already there. So that's a nice confirmation that we're doing things correctly. All right, so we found another one. And again, we repeat. So in the X direction, 0 unknowns. In the Y direction, 0 unknowns. There's nothing unknown in B, or in A. So we move to B. In the Y direction, 0 unknowns. In the X direction, we have 120 and force BC. So we know force BC can be solved. If it's 120 to the right, that means force BC must be 120 to the left. Since it's going to the left, that means it's compressing point B. So that means it has to also compress on the other side. So it has to compress. On point C too. So it's pushing in on point B. It's going to push in on point C. There's 120 here, so it's 120 there. Okay? Now, if I would get stuck, I would use similar triangles. All right, and you can go back to our last video to see that example. This one, however, we didn't even need to use it. So, if I would get stuck, I'd use similar triangles, and then I'd come right back here. I didn't need that, so I'll move on to step 6. So put forces on the drawing and use Pythagorean theorem to solve the diagonal ones. So some of them I know. So for example, I know force AB is 200 and it's in compression because it's pushing on the joint. So when I come up here, I'll say force AB is 200 and it's in compression. All right. Force BC, I see right here, it's 120 and it's also pushing in on its joint, so it's compression. So force BC is 120 in compression. Now AC, if I look down here, I have an ACX and I have an ACY. So what I do is I'm going to use Pythagorean theorem to put those back together. Because remember, force AC is made out of force ACY and force ACX. So ACY is 200, ACX was 120, and I got that right off of here. So 120, 200. And I'm just going to use the Pythagorean theorem to put those back together. So give me a second here, let me get my calculator. And I find that it's 233. And again, I just use Pythagorean theorem. A squared plus b squared equals c squared. So this is 233 on force AC. Now, is it tension or compression? I look back up here, I see force ACX. It's pulling away from this joint. ACY is pulling away. And if I look over here, ACX is pulling away, ACY is pulling away. That tells me it's tension. So I'm going to come right back up here. I'll say 233 in tension. Okay? So that is how we use the steps to go ahead and solve for a statics problem.